Hello everyone, welcome back to my channel. In the last video we learned about what happens when alternating voltage is applied across a parallel combination of capacitor and inductor. So in this video we are going to learn the concept that is Maxwell's bridge. Maxwell designed this bridge to determine the self-inductance value. Here one headphone is connected between B and D, and the AC source is connected across A and C. Here we used R1 and R2, R3, R4 are 4 resistors, inductor value that is L and the variable capacitor that is C. And this Maxwell bridge is modified form of Wheatstone bridge. Here the Wheatstone bridge we learned in PU level. There we determine the ratios of two resistors, or we can determine the value of resistance of a given resistor or the ratios of two resistor by knowing the condition P by Q is equal to R divided by S. By using this condition we can determine the ratios of these two resistors. We can represent R1 divided by R2 which is equal to R3 divided by R4. So this is the condition. So by using this condition we can determine the ratios of these two resistors. But here in this Maxwell's bridge they designed this bridge to determine the self-inductance value. So we know that, let us consider Z1, Z2, Z3 and Z4 are the impedance values for the branches AB, BC, DA and CD, for the branches AB, BC, DA and CD. Here we know that the condition for the Maxwell's bridge by knowing that condition for a Wheatstone bridge network. So here the condition for Maxwell's bridge that can be represented by Z1 divided by Z2 is equal to Z3 divided by Z4. But we have to know that the values of impedance for the each branches. Here we know that Z1 which is equal to R1 because in this branch we are using only resistor and its value is R1 we are mentioning. Similarly Z2, here we are using R2 and C, they are connected in parallel, therefore 1 over Z2 which is equal to 1 divided by R2 plus of, so 1 divided by 1 over, in the sense we can represent J omega C. Similarly for this branch that is Z3, so here Z3 for branch DA we took, therefore R3 plus of J omega L, and then fourthly Z4 that can be written as Z4 which is equal to R4. So this is a condition. Let us consider this one as in equation number 1. Now equation 1 becomes equation 1 that can be written as Z1. In the place of Z1 we have to consider R1. So Z2 divided by Z2 is in the terms of denominator, therefore the whole term that can be written as Z2, 1 over Z2 is equal to 1 divided by R2 plus of J into omega C, which is equal to that Z3 value is R3 plus of J omega L divided by Z4 in the sense R4. Now so if we simplify this term we are going to get R1 into 1 plus of R2 J omega C divided by R2 we are going to get is equal to R3 plus J omega L divided by R4. Now cross multiply this one. So R1 cross multiply R4 we are going to get 1 plus of R2 J omega C which is equal to, just cross multiply R2 into R3 plus of j omega L we are going to get. Now, if we simplify this one or multiply this one, R1 R4 plus of R1 R2 R4 j omega c, which is equal to R2 R3 plus of R2 j omega L we are going to get. Now, by comparing a real and imaginary part, already we know that this which contains a real and imaginary part, and these two are real parts and remaining these two are imaginary parts. By comparing real and imaginary parts, we are going to get R1 R4 which is equal to that R2 R3. Now, if we simplify this one, R1 divided by R2 we are going to get is equal to R3 divided by R4 we are going to get, and this one is one of the condition for the Maxwell's bridge. And even so, if we compare the imaginary parts, and those can be written as R1 R2 R4 j omega c, which is equal to R2 j omega L. So, here R2 gets cancelled, and even if we consider j omega gets cancelled, and the remaining term is L is equal to R1 R4 into C, and this is the one more condition for the Maxwell's bridge, and these two conditions are independent to that each other, and this is about the Maxwell's bridge. So, in the Maxwell bridge, a good balance is obtained by, they mention two conditions here. The first one, by keeping R1 and R2 is kept at a simple ratio, and R3 is varied first until the headphone gives a minimum sound. So, by varying R3 value, by keeping R1 and R2 at a simple ratio, by varying R3 value, we can get the minimum sound in a headphone. And even in a second case, by varying that the value of variable capacitance value, we can get further minimum sound in a headphone. And by doing this 2 or 3 times, by varying R3 and variable capacitance value, we can get a minimum sound, and these are the conditions to get the minimum sound in the Maxwell's bridge. And this is about the Maxwell's bridge and its conditions. Thank you.